how computers evolved. So if you look back, the first general purpose computer was invented in 1940s, which was 60 years ago. It's such a big machine, it's so heavy, and it needs to be occupied for the entire room. And it was designed for the purpose of calculating artillery firing tables for the US Army. And now, after 60 years, I'm pretty sure everyone in the audience, you must have at least a laptop so that you can connect to today's G-Meet, right? So I can even put my laptop in my backpack, I can put my iPhone in my pocket. It's such a small device. So now as computer becomes smaller and more efficient, more accessible, so they no longer limited to big research institute, big tech companies, or even the military. So today, everyone can benefit from and contribute to the open source community. They can work together to develop open source software. In case if you don't know the value of open source software, this is a recent paper Harvard Business School put together. So I'm just going to rate two main takeaways I got from this paper. For $15 billion investment in open source can generate $80 trillion for companies. In other words, $1 investment for open source can create $80,000. And the second takeaway I got from this paper is company would need to spend 350 times in developing software if open source never happened. However, now we talk about large language model, and they're quite different from traditional software, right? When you use a software, click a button, they will generate something for you. But when you run large language model, you need high demand of GPU memory. You need specialized infrastructure. They're not easy to use, even just during inference time. So this is a concrete example of how large language model evolved. So here, x-axis is the year. Y-axis is the performance of the model. The size of either circle or diamond, they represent the number of parameters a large language model has. And as you can see, most recent advanced large language model, which give you good performance, they're pretty big, right? And additionally, with recent models, such as DeepSeek R1 or GPT-O1, those recent models, they require long response to think through the prompt before they give you a final answer. And this is one example. When I was running DeepSeek R1, this too long AD model on the Math 500 dataset. And as you can see, the model needs to break down the prompt into several pieces. It needs to do a lot of chain of thought. It needs to do self-correction. It needs to say, oh, wait, I may be wrong. I need to think about the prompt again. And that's such a long response before giving you the final answer. And the issue of a large language model generating a long response is KV cache. So bear with me if you don't know what KV cache is. I'm going to talk about that in my slides. But for now, just look at this figure. So for long sequence, either long prompt or long response, your GPU memory is mainly occupied by the KV cache rather than the model weights. Because large language model decoding is known to be a memory bound issue, which means it's dominated by data transfer rather than computation. So how we handle the KV cache will decide the inference cost and inference efficiency of running the model. So this is a quick overview of our result. In this work, we introduced a new KV cache quantization algorithm, which we call SQUAD, Subspace-orthogonal KV cache quantization. It allows for int2 or int4 for storing the KV cache. It requires no model training, no additional calibration data. It can run on the fly, and it's grounded in a theoretical framework we developed. So here are some results when we were running our method using DeepSeek R1 distributed llama model on the Math 500 data. On the left-hand side, I'm showing you the comparison with FP16, which is the default data type for storing KV cache, as well as 3 baseline methods, which can also quantize KV cache to int2 or int4. As you can see, our method can improve all existing state-of-the-art KV cache quantization algorithms. For the figure in the middle, here in the x-axis, I'm showing you the batch size. So I gradually increase the batch size till at the point I run out of GPU memory. So as you can see, for the black line, which is FP16, the default data type, you cannot host more than 25 samples in your mini batch because you will clearly run out of memory. But for our method, we can host more than 120 samples in a single mini batch, which enable a factor of 7 increase in the batch size. For the figure on the right-hand side, I'm showing you the latency of running our method compared with running a P16 method. So as you can see, even under the same batch size, let's say maybe 20, so our method can reduce the runtime. And what I mean by runtime is the time you could start from clicking the button of running the large language model till you finish generating responses for all the samples in your mini batch. That's what I mean by runtime. So here, our method can reduce the runtime by at least a factor under the same batch size. And altogether, it enables 5 times improvement in throughput only by sacrificing 2% in accuracy. So this is what I'm going to talk next. This is a quick overview of today's talk. I'm going to start with transformers and attention mechanisms, which are foundation of nowadays most of the large language models. And I'm going to talk about what KV cache is and why we want to do KV cache quantization. In the second part of the talk, I'm going to talk about our method. Again, it's called Subspace-orthogonal KV cache quantization. Finally, I'm going to show you more experiments we have done on reasoning tasks and also long-bench tasks. So I'm going to start with transformers. Probably most of you have seen the figure on the right-hand side, right? You could even see that from either some YouTube videos or some research talks. But that's a figure from a paper called Attention is All You Need, and that's where this transformer architecture was born. And nowadays, most of the large language models, including Llama, Mistral, Q1, and GPT model, they all build upon this architecture. So at the heart of transformer architecture is something called attention mechanism. If you go to a lecture, probably someone will need to spend 1 hour in explaining what attention mechanism is and how that, how transformer architecture works. I'll try to spend only 2 minutes in explaining in the most intuitive language I can imagine. So it's not going to be rigorous, so please bear with me. So I'm going to take this example from our Red Hat website, which explains what the principle of open source is as an example. So what attention mechanism does is it will first break down this prompt into tokens. So think about each token as a word. Then this attention mechanism will generate 3 things for each token: a query, a key, and a value. So each thing is a vector or a tensor in general. So what query is, it's just trying to explain what other tokens before the current token are most contextually relevant to the current token. What key is? So think about key tensor as a summary of the current token. So when you think about Red Hat, the first thing that came to my mind was open source, Linux, or security. So some keywords or some text of this token. So that's what a key tensor is about. And finally, a value tensor is the exact information of your current token, which is Red Hat itself. So what attention mechanism does is it will update the information of each token. So I'm going to take open source, this token as an example. In step 1, it will compute the inner product between the query tensor of open source with all its previous tokens key tensor. So think about this inner product as telling the similarity between the current token and all previous token, right? Because, like for example, when you take open source, clearly open source has a high correlation with Red Hat. Right? We contribute to open source, so the correlation is pretty high. So we get 3.1, for example. But open source might have a neutral correlation with is, right? Because is doesn't give you any semantic meaning. So the correlation is around 0. And finally, open source has a strong correlation with itself, of course. So it will get, for example, 5.1. In the second step, you apply softmax to normalize the score you get to make it a probability distribution. And finally, you use that probability to compute a weighted sum using your value tensor. And that's how you use to update the information for your token open source. You do the same thing for all the other tokens in your sentence. That's what attention mechanism does. It's updating the information for each token again and again. So that leads to the second thing I want to talk about, KV cache. So what KV cache does is it's just storing the key and value tensor for all the generated tokens. So remember that in large language model, when you generate tokens, you do it in an autoregressive manner, in the sense that you generate one token at a time. Then you append your token to your sentence and generate the next token. What KV cache does is it stores all the key and value tensors for your generated tokens. So next time when you generate a new token, you don't need to compute those key and value tensors from scratch. You can just call them from your GPU memory, for example. And that significantly saves the runtime, right? So the way I think about KV cache is like human memory. Right? When you talk with your friends, you never start from scratch, right? When you say a new word or when you start a new topic, you never look back on what you said before. You build on what you mentioned. You recall from your memory. And that's how KV cache does. It's kind of like machine's memory. So remember this figure. That's a figure I mentioned at the beginning of my talk. When your sentence or either your prompt is long or the response is long, so the KV cache can occupy most of your GPU memory rather than the model weights. So the reason we want to do KV cache quantization is because of two reasons. First, it can reduce GPU memory usage, right? Because that's the majority of what you are used for GPU memory. And as a result, that can enable larger batch size for hosting your samples. The second reason is when you reduce this KV cache, you can reduce latency because remember that large language model decoding is known to be memory bound. You spend most of your time in transferring data. So those two reasons motivate us doing KV cache quantization, and that leads to what I'm going to talk about today. So before I introduce our method, I'm going to again look back and tell you how existing KV cache quantization methods do. So what they do is you take your KV cache, say for example, things stored in FP16, and then you convert them into say int2 or int4. Their goal is to make sure when you dequantize your KV cache, you can recover the original KV cache, which means the dequantized key and value tensors, they can approximately equal to the original key and value tensor. The issue is quantization error can accumulate as more tokens are generated. That can cause later tokens to deviate from what you expect the model to output. This is a concrete example, again, using open source principle, as an example. So say the model generates its response. The issue is when you quantize key value tensor for the open source, the last token of your prompt, this quantization error can accumulate and influence every token you generate in the response, right? And as a more concrete example, when we were applying deep cache, which is one existing KV cache quantization algorithm to solve Math 500 equations, what we found was their accuracy was very low. And then we dig into this example, we found most of the time when it's trying to solve the problems in Math 500 data, it starts repeating itself after a certain number of tokens. And the intuition I got was maybe the model forgot the initial question. And because the quantization error accumulates, so after a certain number of generated tokens, it completely forgets what it needs to do, which is solving the math problem. So what instead it does is to repeating itself because that's the only information it has. So that leads to our goal, which is quite different from existing KV cache quantization work. Our goal is to preserve task-relevant information during KV cache quantization to ensure the large language model can generate response as if using full precision or FP16 KV cache data type. So to achieve this goal, we call that how attention mechanism works, right? So you have a bunch of tokens. Each token will give you key, value, and query. When you update the information of the token they collaborating, you use its query tensor to compute inner product with all its previous tokens key vector, right? And then that will give you a weighted sum to update the information of the token which is collaborating. So given this, this fact, when we quantize value tensor, we follow exactly the same goal with existing paper, in the sense that we make sure the value tensor can approximately be equal to the dequantized value tensor. Our main innovation is to give a new algorithm for quantizing K tensor, and that's building upon two observations we have in the paper. The first observation is when you look at attention mechanism's output, the way you use K tensor is to compute inner product with all the tokens after the current token with their prior tensor, right? That means when you quantize K tensor, the main goal is to preserve their inner product with future tokens query tensor, right? That's the main goal we should do. Rather than just minimizing the difference between the original and the quantized K tensor. So this observation leads to the main optimization problem we are trying to solve. So here, let's take open source this token as an example. So I'm going to quantize the K tensor for this token. The way I quantize this token is I look ahead. I look ahead of what tokens we are going to generate. Let's say maybe software all the way to collaborating. So those are the tokens after open source token. So I'll concatenate those tokens query tensor as a matrix Q hat. Right, that's again the queries of subsequent tokens after the current token to be quantized. Then I formalize an optimization problem. So this optimization problem tries to minimize the quantization error so that this error is orthogonal to the query of all the subsequent tokens. Because if you can make sure this orthogonality, you can make sure your quantization error doesn't influence your attention mechanism at all. And finally, because we want to quantize this tensor to int2, for example, that's the last constraint we propose in this optimization. But there are two challenges when we try to solve this optimization. The first challenge is when you quantize the current token, you never know what will happen next, right? You are never able to look ahead. Because if you are able to do that, then what would be the point of doing quantization, right? So the first challenge is we don't know the matrix Q hat. We don't know the query tensor of future tokens. The second challenge is the optimization problem you see from the right-hand side is a mixed integer program, which means it is a combinatorial optimization. It's very hard to solve. It's different from linear programs, different from convex optimization. So it's in general intractable to solve for getting a global optimal solution. So next, I'm going to propose some solution for those two challenges. The first challenge is recall we don't know future tokens query tensor. Our observations are first, query tensors, they tend to lie within a very small subspace. And this space has much lower dimension than the hidden dimension of your query tensor. And the second observation is this subspace can be derived using tokens only from your prompt. So even if you don't know what you are going to generate in your response, that's completely fine. You can learn from your prompt token only. So to make it intuitively or to illustrate those 2 points, I'm going to take one example from, again, the Math 500 dataset. And I'm using Llama 3 DB model to complete its response. Remember that each token will generate a query tensor in the attention mechanism, right? Now we collect queries from each one of the tokens from both your prompt and response, right? That will give you Q1 to Q1. So each one is a query tensor, each a query vector. Then we apply SVD, which is called singular value decomposition. We take the top k singular vectors. So that's kind of a way we do dimension reduction, right? Because you have so many tokens from your prompt and response. So we want to do dimension reduction. We want to take the k most important directions that are most relevant to your context. So that's what we do by doing apply SVD here. Finally, I take one token, let's say, for example, fraction pi over 2, from the response. This is denoted as Q, so we denote its query tensor as Q. We compute its deviation from the subspace we construct. So the deviation is here. So how far this query tensor is away from the subspace. That's what I mean by deviation. So similarly, I construct another 3 subspace. So those another 3 subspace, they're constructed in a similar way. The difference is for the second one, prompt only. I only use token from my prompt. I don't look at response token. So I use those tokens, those prompt tokens, to get my query tensor and again apply SVD to get top k most important directions. The third subspace is by taking a completely different sentence from the same dataset, from the same Math 500 dataset. Again, I apply SVD to do dimension reduction to get top k most important direction. The final subspace is obtained by using a completely different dataset, which is called quality dataset. It's a document Q&A. It's nothing to do with mathematics. Again, I apply SVD to compute the top k directions. I take the same token from the response, which is fraction pi over 2, to compute its deviation from the subspace. So the token doesn't change, the subspace changes. And do you want to get which subspace incurs the smallest deviation error and which one has the highest deviation error? Anyone wants to have a guess? Yeah. Different dataset that should give you the highest deviation error, right? Yeah. So that's my intuition initially. So intuitively, we would think a different dataset because that's nothing to do with mathematics, right? So it shouldn't include my fraction over 2, this tokens information, right? You should have the highest deviation. And in contrast, when you use tokens from both prompt and response, the one on your left-hand side, that should give you the smallest deviation, right? Because that even includes the token fraction over 2 pi over 2, right? That includes that information. So that's the intuition we had initially. But then we run some experiment. This is the result we got, which is quite surprising to me. So the result is the deviation error for prompt plus response is roughly the same with prompt token only, which is roughly the same with a different sequence. And it's slightly lower than the deviation you get from using a different sequence. And that's what you can see from the figure on your left-hand side. So let me walk you through this figure. So in the x-axis here, remember that I apply SVD to compute the top k most important directions, right? So here I'm varying the k. Because I'm using Llama 8B model, so the hidden dimension is 128. So if k is equal to 128, I should perfectly include my query tensor, right? Because I'm spanning the full space. And here the x-axis is the deviation error. So as you can see, the blue curve, which is, I use prompt plus response token together to formalize this subspace. And as you imagine, as you could think about, that gives you the lowest deviation error. But if you look at the green curve and the yellow curve, they're quite similar to prompt plus response, right? So that means even if I don't know my response token, I can still use my prompt token, or I can use another sequence from my data set to form this subspace. And with high probability or with a very small error, that subspace is roughly the same with using the entire sequence to form this subspace. So again, that's one of the main takeaway, which is using prompt-only tokens, which is available even before the decoding phase gets started. Or you can use query tensor from a different sequence from the same data set that doesn't increase the subspace deviation error. So that leads to a solution we give for challenge 1, which is we don't know query tensor of future tokens. The solution we give is we take each one of the tokens from the prompt, we compute their query tensor. Then we collect them all together and apply SBD to compute the k most important directions. That's what we get for this Q-hat matrix. Okay, so first challenge solved. How about the second challenge? How can we solve this combinatorial optimization problem? So the solution we give is an iterative algorithm. And more specifically, at the first iteration, we quantize the first element, and then we update the remaining element of your k tensor. We do it step by step. At the tth iteration, since we already quantized the first t-1 elements, so we keep them unchanged. We only quantize the tth element of your query tensor. After that, we update the remaining elements. And more specifically, the way we update the remaining elements is by solving another optimization problem. So here in the objective function, we make sure when we update those elements, we make smallest change to the current elements. That's the first term in the objective function. The second term is when we update the elements, we make sure the quantization error can have minimum impact on the attention mechanism output, and we achieve that to make sure the residual is orthogonal to the query subspace Q-hat. In the constraint, we have two constraints, and the first constraint is, remember that at the tth iteration, the first t-1 elements have already been quantized, so we keep them unchanged. We don't want at the current iteration to change anything we have already been quantized before. So that's the first constraint we impose. The second constraint is, remember that in the current iteration, we quantize the t element, and then we update the remaining elements. So the quantization of the t element is imposed as the second constraint of this optimization. So the main technical innovation of this work is we prove that this optimization has a closed form solution in the sense that you don't need to rely on any off-the-shelf optimization package. You don't need to run Cplex, you don't need to run Groovy. No, you just take our closed form expression to update your query tensor. That's very efficient because we have optimized the way we update those query tensor. So that's the mathematical formulation we give, and that's the key innovation. But if you ask me to explain our algorithm in the most intuitive language, and here's what I will tell you. So what this iterative algorithm does is it will ensure every time we quantize one element of the key tensor, we make sure the resulting quantization error has minimum impact on attention mechanism's output, and that's achieved by the second objective in your the second term in your objective function, which is the orthogonality regularization function. So that's the kind of an overview of our algorithm. And again, if you want to check technical details like how we prove this theorem and how we make this algorithm efficient, please make sure to check our paper. And again, it's called SWOT, Subspace-orthogonal KV cache quantization.
And how we make a video about it.
Okay, so I have already shown you some experiments we have done on the 500 data set, but we have more experiments we have done on this paper. So the first result I want to show you is, as I mentioned earlier in my talk, so the key difference between our algorithm and existing algorithm is they only focus on preserving the fidelity of your quantization, But in our case, we look at attention mechanism. So our goal is to make sure the attention mechanism can generate similar output as if we're using the full precision KV cache. So in this experiment, I'm showing you the comparison between existing algorithm and our algorithm in preserving attention scores. So here, each score is the difference between using original data type and quantized k-tensor. So if you get a question.
Which method are you showing here?
Yeah, so it's Kiwi.
Okay.
Yeah, great question. So okay, so here, so on the so here, so each color represents the value or the difference between the attention score. And if you get a smaller value, say 0, that means you can fully recover the original attention score. And as you can see, using our method, so especially here at the beginning of the token, you can significantly reduce the attention score compared with existing methods.
What is the x-axis?
Oh, yeah, great question. So here, let me think. So x-axis is your
Both are positions. It's all 12.
yeah. So one is query tensor of your token, another is k-tensor of your token. So here I'm computing the inner product between each token's query tensor and other token's k-tensor.
The attention score is.
Yeah, the attention score. So the reason I only show you the lower rectangle is because people call it causal language model. I mean, I don't like this terminology. It's nothing to do with causality. Yeah, but that's how people call it. So basically, when you update the information of your current token, you never look ahead. You only look at the previous token's information.
Is that be cheating?
I mean, yeah, that's their argument, right? You don't look ahead.
Autoregressive.
Yeah. So okay. So that's the first experiment. And the second experiment, as I mentioned to you, is a reasoning model, which is a deep skilled llama model. So we apply that to Math 500 data. And here we compare our method with 3 baselines. The first is Kiwi, which is a paper published last year in SML. And the second method is a paper called JIR. I think it was a workshop paper. The last one is called Zcash. It's a paper published last year in Inference. So comparing with those 3 methods, our algorithm can achieve higher accuracy compared with them. And beyond Math 500 data, we have done a lot of other reasoning tasks we chose from LLM. And most of them are suggested by existing papers like Kiwi and JIR. So all of them run GSM 8K, for example, which is a kind of an elementary level mathematical data set. So here, the first column, I'm showing you different methods, right? So we compare with Kiwi, JIR, Zcash, and squat and squat pre are all our methods. The only difference is squat pre is we apply quantization before applying rotary positioning back. And squat is we apply quantization after rope. So here I'm choosing another 3 models. The first one is Llama 2.7b, the second is Llama 3.18b, and the last one is Mistral 7b instruct model. So the second column here, I'm showing you the KV cache size, which is a comparison between the GPU memory used for saving the KV cache for using our method compared with the FP16, the default data type for saving KV cache. And as you can see, we kind of control all the KV cache size between our method and existing baseline to be roughly the same for fair comparison. So they all reduce KV cache to roughly 20%, which is a lot. So here, among all the models and all the tasks, especially on GSM 8K and GPQ and BBH, which are known to be quite difficult reasoning tasks to solve. So we all achieve higher score than existing KV cache quantization algorithms. And the results look even more promising when you apply those quantization algorithms to easier tasks. What I mean by easier tasks is, say, for example, tasks we chose from LongBench, which is a long context benchmark task about document Q&A and document summary, nothing to do with complex reasoning. So here I'm showing you 8 tasks we chose from LongBench. And again, I'm comparing our method with existing baseline and 16 default data type. And as you can see here, on the last column, which is the average accuracy among all the tasks. So most of the time, we can achieve near lossless accuracy, right? So our average accuracy can roughly match the accuracy of using FP16. So this is quite surprising because we reduce the KV cache to using int2, which is a very aggressive data quantization or data type, right? And still we can achieve quite, I will say like near lossless accuracy on those easy language tasks. Yeah, Patrick.
Yeah, for the underlying formats, you mentioned int2, and then it's per token, right?
What is it?
Per token on the KV cache, right?
Yeah.
Yeah, and then is it asymmetric, symmetric?
What do you mean by asymmetric?
Oh, it's just where your 0 points end up being.
Oh yeah, great question. So yeah, so let me clarify a bit more. So for value tensor, we do it per token, but for key tensor, we do it per channel. And then for 0 point and scaling factor. So for value tensor, for lemma 3B for 3AB model as example, because the hidden dimension is 128. So we choose the group size to be 32. So 32 elements in the in the value tensor, they will share the same group 0 point as scaling factor. For the key tensor, we do it per channel. So each 32 key tensor, and among each channel, they will share the same 0 point and same scaling factor. And we do it for all existing baselines for GR and Kiwi. We do the same. We keep the group size to be 32, and all of the methods they keep something called residual buffer. So which means you keep. In our case, we set it to be 32. So 32, the most recent tokens, we save them in full precision. So everything, all four baseline and including our method, we choose the residual to be 32 as well. So everything like means just for fair comparison. Yeah.
That was just on one of the sides. Was it key or value? I
Yes.
forget which one needs to
Yeah,
be.
so value, we do it per token. Key, we do it per channel.
Yeah. But I mean, in terms of the buffer that you're keeping, that's
Yeah.
just on the
Good question. So, okay, let me elaborate more. So for key tensor, we keep 32 residual buffer, and every time you hit 32, you quantize everything. You set this residual buffer to be an empty set. For value tensor, we always keep a 32 residual buffer. So every time you get a new token, you just quantize the last token, but you keep the residual to be 32 always. Yeah. Okay, so that leads to a quick summary of our work. So at the beginning of this work, I started with recalling or looking back how computer evolved. So as I mentioned, nowadays, after 60 years development of computer, and everyone in this room, you must have at least one laptop at home. So that makes people easy or to contribute to the open source community, right? And this is a paper from Harvard Business School which shows the value of doing open source software. However, for large language models, they are becoming bigger and bigger, which create a barrier for the open source community to benefit from and contribute to. And additionally, with reasoning models, which generate a long response. So the most of your GPU memory will be occupied by the KV cache. So if you don't handle your KV cache carefully, you will easily run out of memory, and you will have a high latency when calling those models. So to address this issue, in this paper, we propose a method called SWAP, Subspace-orthogonal KV cache quantization. And the key idea is we want to make sure the quantization error is orthogonal to the query tensors. So that's the way we reduce the quantization error's impact on attention mechanism's output. And so when we were doing this project, when we implemented our algorithm, we reused a lot of code from the open source community, and especially for the paper named Kiwi, which is a baseline we compared with in the paper. We reused a lot of CUDA code we wrote in the paper. So we benefit from the open source community. And as a return, we also make everything open source. Everything you have seen today, all the technical details, all the proofs, all the results I have shown, you can find them from our archive paper and also the GitHub repo, which is, the link is given below. So we benefit from this society and we contribute to this society. And if you want to see more interesting work which is happening in this group, so please feel free to check our website. And there are ongoing works. There are also a lot of open source code in this in our GitHub repo. So finally, I would like to conclude this talk by saying, with big models come big responsibility, and we, the open source community, can help. Thank you so much.